Hello, everybody. Welcome to the afternoon tutorial sessions at L4DC. Hope you're not wet. You can get more wet later. There's more rain coming. All right, so it's my pleasure to introduce, first, Luis Chamon, who is going to be, starting the tutorial. This is a tutorial that's organized together with Miguel Calvo Fulana from the University of Pompeu Fabra in Spain. Luis is in Stuttgart in Germany, Santiago Paternine from Rensselaer Polytechnic in the States, and also Alejandro Ribeiro from University of Pennsylvania in the States. So we are all appreciating that it's actually a multinational, presentation here. And the title is very interesting, Learning Under Requirements. So I'm full of questions about it. So I'm not going to keep any more time. Please go ahead.
Thank you. Let's see if I can get this to. Should have done this before. Thank you, KG, for the introduction. So as KG mentioned, we're going to talk today about learning under requirements. It's a long topic, but luckily the tutorials this morning sort of gave us a. It's going to take a little while for me to make it, but it's okay. I don't know. Let's see. Gave us a lot of prerequisites in a certain sense to the part on reinforcement learning, also to a lot of talks that we're going to talk today about duality. So a lot of it was mentioned this morning, at least in certain contexts. It's going to help us, go a little bit faster. But the idea is, again, as Wolfram mentioned this morning, is to be a tutorial. And so, we'll have space for questions if you have them. And we really actually want to go a little bit slower on some of the topics so that you can actually get a good idea of what is happening. So I want to start, as people trickle in a little bit, just with a very soft introduction as to, the main problem that we're going to discuss today throughout this 3-hour tutorial. And this is organized essentially in 2 parts, right? So before the break, we're going to talk about the supervised learning problem. This is going to be a lot about settling the main theory that is going to allow us to develop everything, all these methods that we're going to talk about. And we're going to start with constrained learning theory. That's going to be, Alejandro is going to talk to us a little bit about that. Resilient constrained learning, and then robust learning. Then we're going to take a break, go for a coffee, and we'll come back with the parallel theory in reinforcement learning. Okay, there's a lot of similarities, but there are enough differences that it's worth taking in a different scale, and this is going to be covered by Santiago and Miguel, right? So to begin, just before I continue, you can scan this QR. This is the website for this tutorial. You have all the slides there. Okay, so you can go. I'll show it again at the end. Don't worry about it. So you have all the slides and information about the material that we covered at least today. So let's talk a little bit about why should we care about learning under requirements, right? The idea of requirements for anybody that has done engineering is the basis of every system engineering project, right? So we start by setting requirements based on which we then collect data, build models, and optimize operational settings, right? So what we mean by requirement here is what is meant by required in system engineering, which means it's what we call shall statements, right? So this defines essentially the constraint space. It's the thing that we get to decide what the system has to do, right? This is to be contrasted with what are called should statements, which are more considered objectives, right? Okay, so these are things that essentially the system achieves or that we want to optimize over in terms of the system, right? These 2 things put together are the basis of system design. Now, obviously, you can turn any shall statement, the system shall be a certain level of safety or a certain level of robustness, into the system should be robust, right? So an objective and a requirement is very problem-specific decision, which one is going to be which. But we want to be able to tackle both things because they have substantially different goals when we are designing a system in terms of in terms of expressivity, right? What we're trying to do. So the main point here about learning under requirements is that, the promise to a certain extent of learning here is that we can take this classic, let's say, traditional system engineering cycle and bypass a part of it, right? And take us from data to operation directly, right? With little to no human intervention. So the idea of statistical learning is to go from data to the system that we want. And the main point of this is that, we still want to have the requirements there somehow, right? That's the big difference that we have between constrained learning and, let's say, unconstrained learning, is that we want to satisfy requirements at the same time as we are learning, solving a learning problem or solving a data-driven, let's say, problem. And just to formulate what we mean by constrained learning specifically, we want to take a classical learning problem, which is defined just as a minimization of an expected loss, and we want to add constraints. That's it, right? That's the whole tutorial today is going to be about solving this type of problems. Problems where we want to minimize an expected loss, a statistical loss, subject to specific statistical constraints on other expected losses, with the difference that we're not going to have access to any of those distributions, right? Everything is going to be data-driven. That's the whole problem, the formal problem that we're interested in solving today. And I want to start by talking about, this sort of duality that came up this morning, right? Between this problem, this constrained learning problem, and its, let's call it this regularized or penalty version, right? This is a duality that we are very used to seeing, right? A lot of problems in, say, if you go to machine learning, a lot of the ways these constraints are tackled is by, adding them to the objective somehow, and then choosing some of these parameters in a way that makes sense or doesn't make sense, depending on what you're, right? The problem that we have here is non-convexity, right? We already sort of heard a little bit about this morning. And non-convexity means that there may not even exist parameters, lambda and mu here, that give optimal and feasible solutions to that problem. And even if they exist, they might not be easy to find, right? Which is a big contrast to convexity, where we can, under very mild conditions like Slater's condition, we can show that strong duality holds, and therefore there exist these parameters, and they're often not too hard to find, okay? So the big advantage for us that we're going to hopefully manage to show and tell you, both prove and show you, is that using a constraint formulation as opposed to this, let's say, regularized formulation has a lot of advantages, both in terms of theoretical advantages, in terms of guarantees, but also in terms of performance. Okay. So just to give you a couple of examples, I'm going to go through those very quickly, of applications of this problem. Why should we care about this at all? Okay. So these are essentially 5 applications that we're going to see throughout this talk. Over the next 3 hours, we're going to go through them as examples of the theory that we developed. I just want to give you a brief overview of all of them so that you can see how, this problem that I wrote here sort of can be used to formulate a lot of problems in these settings. And later on, I'm going to go very fast now, maybe, so if you don't catch everything, that's okay. Later on, we're going to go back to all of these and explore them in a little bit more of detail, right? So let me start with the problem in fairness, right? The problem in fairness is this problem that, we want to either predict some sort of recidivism in our problem, right? So we want to predict recidivism or predict whether an individual makes more than, let's say, $50K. And the issue is that the data is very biased, and that bias gets, amplified even in the solution that we see when we solve an unconstrained optimization problem, right? And we want to sort of mitigate this bias in the constraints that we have. So we want to do fair learning. And, we can think about mitigating this bias in this prediction. So the amount of time that we predict recidivism, right? We can write that as a constrained optimization problem where we minimize, obviously, the prediction error. That part is just the accuracy. We want the most accurate method but only among those classifiers that have low prediction disparity, which means that we predict recidivism within each group roughly at the same rate as we predict recidivism across the population. So this is sort of the definition of fairness that we have here. It's not really our job in this talk to, argue for this or another definition of fairness. So all we want here is, okay, if this is what you want, how can you go about solving it? Okay. So another definition of fairness, or another thing that could be considered as a fairness, is a form of invariance, right? So we want the most accurate model that if I were to say change from male to female, all other things kept equal, the prediction shouldn't change, right? And this can, again, be written as a constraint, an expected value of some loss. In this case, between the prediction that I get out of just the data that I have and some modification of the data that I can choose what it is, and you can have many different ones. Okay. So another problem is that of which is related to fairness, but in a completely different way, is in federated learning or distributed optimization, right? In this case, what we want to do is sort of, we have data distributed among different computers, among different nodes, and we want this data to, and want to learn a model, but without exchanging data between nodes, okay? So this is the idea here. And how do we do that? We set up this problem by essentially saying, you know, every one of those nodes has a loss, local, and I sort of want to minimize the aggregated loss of all of them. So the average of all those losses, okay? And this we can do, you know, in a distributed way. That's fine. The issue with this is what happens when certain nodes have very different distributions than other ones, right? So for example, for these two nodes, they will perceive a loss because I am only minimizing the average loss across nodes. They will perceive a much higher loss, right? Because they have a very different data than the other nodes. Essentially their error gets washed down in the average. So we want to guarantee that this doesn't happen. We want to guarantee that each node also perceives a good, you know, also locally, not only on average globally, we want to do well, but we also want each node to be well for themselves. And this we can write again as a loss disparity, which is very similar to the first loss that we had written, right? So the first constraint we had written, where essentially the loss of each node has to be not much larger than the average loss that I achieve across everybody, okay? So this is again a measure of how disparate the, let's say, the accuracy or the performance is across nodes. It's a similar problem there. In robustness, as you know, it's a problem that is very similar here. In our case, we can talk about adversarial robustness, right? In learning, we know that trained models on clean data, let's say, are very brittle. So very small perturbations of the input can lead to large perturbations of the output. And this is something that we want to avoid, right? So how do we avoid that? That's essentially, we want to do well on average on the data that is clean, while also being robust to perturbations, okay? So this is, again, same problem. We just want to minimize the error, right? Not the accuracy, maximize the accuracy, so minimize the some loss function, while being sure that as I perturb the data in a worst case fashion, right, I still don't change too much. I'm within a certain level. This C is essentially my decision of how robust I want something to be, okay? And the idea here is to find the best classifier among those that are not and that are robust. This idea of worst case optimization also pop ups in other problems that are not necessary. I mean, are related to robustness, but not exactly. For example, in the problem of, in this case, learning a smooth controller that imitates, you know, another policy based on limited number of trajectories. So what I want to do here is essentially look at, you know, pairs of state actions that I know are good, and I want to sort of imitate that controller. I want to learn to reproduce that. Obviously, I only have limited trajectories, so I have no idea what has to happen if I were here, for example, or in other places of the space. So what I want to do is to use smoothness as a way to sort of get additional information about what I should do in states that I haven't seen the action, right? So here the problem that we want is the one of, you know, minimize some sort of regression error between state action pairs that I have, but also at the same time, I want to be sure that I am smooth, you know, but not smooth everywhere in the natural way, but smooth on something that is a little bit more tricky. The distances of my measure of smoothness is going to depend a little bit on the free space, right? I don't care about having the exact same action on this side and this side, because those are actually 2 points that are very far away in the free space. So I want to take into account this as well. Something we'll go back to. If this isn't clear, that's okay. That's going to get a little bit more clear later. In terms of safe learning, now we get to a little bit more of what we'll be talking about in the second part, which is reinforcement learning. Here, what we want to do is say, learn to navigate a space, right, while not hitting objects. Quite a direct problem. We want to do that using reinforcement learning. And again, we can write that as a constrained reinforcement learning problem where I maximize some sort of reward that represents the task of, you know, reaching the goal, subject to the probability of me colliding with obstacles being small, or said another way, the probability of me remaining in the free space being high. Okay? So this is again a constrained learning problem that we want to solve. And finally, wireless resource allocation. This one I'm going to spend 1 minute more than it would because it doesn't really look like a reinforcement learning problem, but it is. Okay. So the idea here is that we want to sort of optimize the transmission power between elements to achieve a certain communication rate, right? In this case, what I mean by communication rate is just that you get to transmit messages at a minimum number of, let's say, bits per second. And this is defined by the power that I input into the channel and the value of the channel, right? So the channel sometimes is very bad, and in which case I can put as much power as I want inside and nothing gets to the other side. And sometimes it's very good and very little power would transmit it, right? So I just want to be able to essentially manage these two things. So I can think of the power as the action, the channel as the state. I just want to get like a point how much power I should put depending on the state that I'm in. Okay, so this is the same problem as before, and I can just minimize the total transmit power subject to, my rate of transmission being a certain value. And I can even make this problem a little bit more complicated by adding, say, some sort of battery on each of the nodes. And rather than minimizing the maximum power, I actually want to minimize the probability that I deplete the battery. Okay, so this is sort of like a large number of problems that we can solve. There are many more, but these are the ones that we're going to focus on today to explain, to sort of give you examples of what can be done with this theory. And with that in mind, I'm going to give the microphone to Alejandro that is going to be talking about constraint supervised learning.
Thanks for the intro, Luis, and thank you all of you for being here. There's something that I know from experience is very difficult, which is to pay attention to a talk at right after lunch. But there's something more difficult than that, which is to give a talk right after lunch. So don't expect me to be sorry for you. Luis gave you a great introduction to what learning with constraints is. And, like the one message that you should take from that is that if you are doing learning without constraints, you're missing an opportunity, right? Because, after you think about it, there are way more problems where we want to impose constraints and problems where we don't. But, there is also a reason why learning with constraints is not so popular, not so widespread, which is that, we don't really understand much the theoretical properties of these problem formulations. We don't really have many algorithms. So let me give you what are our first attempts at developing a theory of constrained learning, and let me tell you about what are the algorithms that you should be using for solving these constrained learning problems. Just as a reminder, here I have the same mathematical formulation that Luis showed you earlier on. So we have the minimization of a certain objective subject to a bunch of constraints. And these constraints come in two flavors, right? They could be population averages, or they could be point-wise constraints. Like a population average is, I want this to happen over my data distribution. A point-wise constraint, or like an individual constraint, is I want this to hold for everybody in my population. Okay, so this could be a formulation of average safety or average fairness. This could be a formulation of everybody safety or everybody fairness. And there are some mathematical restrictions here, but the ones I should call attention to is the fact that these functions L and G, I am not going to assume they are convex, and I am not going to assume that the parametrization F theta is convex either, okay? Because otherwise this would be convex optimization. Convex optimization is easy. Learning, unfortunately, is not convex. That makes it more difficult. Now that's the problem that we can solve, because that's the data that we have. The problem that we want to solve actually is this one, right? So we want to solve the problem over the statistical distribution of the data. The reason why we do not solve this one is because we don't have access to the probability distribution. And that motivates the question, right, of whether the empirical converges to the statistical. Now, if I eliminate these constraints, you know that this is true. That's, Babnik-Chervonenkis theory. That's learnability theory. That's the concept of probably approximately correct. So we know, and even more basic, that's the law of large numbers at the end of the day. We know that if we have sufficiently large numbers of samples, this problem will converge to that one, provided that we have some conditions on the parametrization. But the moment we incorporate constraints, we don't know that this is true anymore. So that's one challenge here. A second challenge is computational, right? Well, let's assume that we are able to prove that this problem converges to this one. How do we actually solve it? And as it turns out, both of these are complicated questions to answer. So let me try, and give you, give you the results that would allow you to answer these two questions. And for simplicity, I am going to stop writing the point-wise constraints. You can treat them in a very similar way. I'm just trying to simplify notation for the rest of the talk. Okay. Now let's here talk about constraint learning theory. Then we'll talk about algorithms, and I will close my part of the day by talking about resilience. Now, the constraint learning theory asks the following question. Okay, so here we have our empirical problem. Does it converge to the statistical problem, yes or no? Okay, if we go again to the unparameterized problem, to the problem without constraints, we know that in the problem without constraints, the empirical loss converges to statistical loss. So, maybe this is the picture that you want to have in mind, right? So, most of the samples are going to be, close to the predicted empirical average. Now, when you have constraints, the picture changes a little bit. Now you have to have this two-dimensional picture in mind, right? And there's two things that you want to happen here. You want your objective to be close to the optimum, and you want your constraints to be close to satisfied. And I have highlighted two things in red here. The first one is that when we say close to, we mean close to in absolute value, okay? And that absolute value is important that I highlighted because in standard learning theory, this is not there because it's impossible for this quantity to be smaller than that one. But in constraint optimization, this could happen because you're violating the constraints, okay? Therefore, learnability in constraint learning means we are close to the statistical objective in absolute value, and we are close to satisfying our constraints. Okay, now how can we go about analyzing this problem? Well, the first question that you should ask me is, okay, are you making too much of an issue of something that is not actually an issue? Meaning, maybe you can just simply show that PAC learnability implies PAC C learnability, right? That if a problem is learnable without constraints, it is also learnable with constraints. Well, the answer to that question is no. And here there's a counterexample, and I'm not going to go through the details of it because that will be a little besides the point, and we are leaving this for your reference here. But essentially, for those of you that are familiar with optimization, we are constructing a critical problem here. It's a problem that if you were to perturb it a little bit, it would become infeasible. Okay, and that's suffices to show that there are problems that are PAC learnable, there are parametrizations that are PAC learnable, which are not PAC C learnable. Which means that we need to, investigate a different, way of understanding generalization, okay? I cannot simply say that because unconstrained optimization problems are learnable, constrained optimization problems are learnable as well. Let me leave you in this suspenseful note for a minute, and let me talk a little bit about computational issues, which is, can we actually solve these constrained empirical problems? And in order to do that, I'm going to do something that you should be expecting me to do, which is that I'm going to try and leverage duality, okay? So this is the constrained optimization problem that we want to solve. We want to solve it in the dual domain. Well, that's the Lagrangian dual formulation. And in general, we do not, or we cannot claim a strong duality here, right? If we knew that these optimization problems were convex, we knew that these two problems would be equivalent, but we do not have convexity. We do not have convexity for two reasons, because L and G, maybe they are not convex, and furthermore, F theta, the parametrization is not convex either, right? That thing could be a convolutional neural network, a graph neural network. It's not a linear parametrization or something easy. Which means that we do not have duality either. And here I am reaching what you could consider the low point of this talk, because I introduce these problems and I hope that Luis convinced you that these problems are very interesting, right? And then I ask you two questions. Does this generalize? And I tell you, well, not necessarily. Second question is, how do I solve them? And you know that the dual domain will play a role in that solution at some point or another. And I told you I can't go into the dual domain. So am I wasting your time? Well, maybe, but I hope not. Yeah, always good to have a friend in the audience. Yeah. No, I'm not. So let's see, what is it that we can do. So here I am showing you two things that are a little weird, okay? So this is the problem that I told you, the one that I would like to solve but can't because I don't have access to the probability distribution, okay? So this problem is statistical and primal. And over there, I am writing a different problem, which is the empirical dual, okay? So the problem is empirical because it's over data, and it is written in the dual domain. And these really are the two problems that I would like to relate, okay? And the way in which I would like to relate these two problems is the following. I would like to say that these two are closed, that would be packed learnability. And then I would like to say that these two are closed, that would be strong duality, and then I could close the loop in that way. But I told you that both of these arrows are false, okay? It's not true that we can have packed learnability. It is not true that we can have a strong duality. But here, there's something strange that I can do, which is I can forget about the parametrization for a minute and introduce this other couple of problems, which are primal and dual, but unparametrized, okay? So I'm doing something strange, guys. I'm getting this parametrization here, and I am removing it. And this may sound strange, but it actually has a very good reason for being done here. And the reason is the following. If we have convex optimization, the primal and dual are equivalent. If we have non-convex, finite dimensional optimizations, primal and dual, they are often different. But something weird happens in the limit, which is that if you consider non-convex optimization problems in infinite dimensional spaces, it is very often the case that in these problems, the primal and the dual are equivalent. And the best known case of this is sparsity. This is an unusual view of sparsity, but one that maybe if you've seen sparsity before, you're able to understand. So here I have a sparsity logistic regression formulated in a discrete space. And here I have a sparsity formulated in a continuous state space. Instead of having a sum over this integral, I have a sum over this indicator. Here I have an integral over this indicator function. Okay? And this problem is known to have, that one here, sorry. This problem here is known to have no duality gap, and that's the reason why, we can show that's the reason why we can do a sparse reconstruction when the number of samples that we observe is large. And that holds in this problem as well, okay? This is not a proof by any means. The proof is included in our papers, but I wanted to give you the space from which this proof comes from. And indeed, it is possible to prove that if you consider the primal unparametrized, that is equivalent to the dual unparametrized. And now we are good because we can now undo this wheel and come back up. The first thing that I'm going to do is I'm going to say, well, this one is unparametrized, this one is parametrized, but if the parametrization is rich, these two are close, and these other two are close because now I am in the realm of unconstrained learning problems. Now, all of that can be summarized into a theorem, which is highlighted here, which is that the so these are the hypotheses stated formally. Sorry, I have an older version of the slides. Here is the result that I wanted to highlight. So first off, the optimality gap is small, and second, the constraints are nearly satisfied. So let me see, I lost my track a little bit, so let me make sure that I get it back and I don't confuse you. So let me tell you what was important here. Let me give you kind of like a summary of this talk. The two problems that I want to solve are these, guys. So I want to be able to say it is possible for me to solve that optimization problem in lieu of this one. Okay, it is possible for me to solve a problem that is dual and empirical and obtain solutions that are close to the solutions that I would obtain if I were solving the problem that is statistical and primal. However, I can't go through the empirical primal for two reasons. I don't have pack learnability, and I don't have a strong duality. I, however, do something strange, which is I introduce this problem, which is unparameterized, and in this unparameterized problem, leveraging results that ultimately come from sparsity theory, it is possible for us to show that in that unparameterized problem, we have no duality gap. Having no duality gap, we can move here by considering the richness of the parametrization, and we can move up by considering a standard statistical learning theory because there's no constraints relating these two problems anymore, right? These are two unconstrained optimization problems. And that leads to this theorem here, in which we show PAC-C learnability, and this PAC-C learnability, as I told you before, has two components. First one is optimality, and this optimality is controlled by this quantity epsilon 0, which is the richness of the parametrization. That comes from the first approximation, right? I mean, the relationship between the unparametrized and the parametrized. It also depends on this other quantity epsilon, which comes from the second step, the one relating the parametrized empirical with the parametrized statistical. And that quantity epsilon is also describing the lack of feasibility in the constraints, right? But remember that as n grows, this epsilon is small, right? So there's two things happening here. As the number of samples grows, this blue epsilon grows to 0. As you introduce a richer parametrization, this red nu is the one that becomes small. Now, finally, the most interesting aspect of this result is the appearance of this lambda, which is the one norm of the optimal Lagrange multiplier. And that's something that you should have expected to be there because that's what characterizes the requirements difficulty. In the counterexample that I show you for PAC-C learnability, what fails is that this Lagrange multiplier can be very large. I mean, it can be infinite, and that's the reason why we don't have PAC learnability implying PAC-C learnability. Well, this was the intense part of the talk. I hope I did it a little bit of justice. There's a couple of remarks that I want to make about these results. The first one is the following. In a standard learning theory, there are two axes of complexity, which are the sample size and the richness of the parametrization, okay? In constrained learning theory, there's a third axis of complexity, which is the complexity of the requirements, and that is unique of constrained learning theory, okay? Meaning, if you are going to work with constrained learning, there's something very important that you should keep in mind, which is that it's not enough to have a lot of samples and a rich parametrization. You also need to be able to formulate a problem in which the Lagrange multiplier is contained, in which the complexity of the requirements is contained. The other remark that I want to make is that, you know, I told you that PAC-C learnability and PAC learnability are different, but in reality, the theorem shows you that they're, you know, more or less the same. I mean, the only caveat here is that you need to have a parametrization that is sufficiently rich, but in general, it is not unfair to say that learning with constraints has more or less the same complexity as learning without constraints. And finally, just because, you know, for those of you that are theory inclined, you know, it is important to realize that PAC learnability and PAC-C learnability are different. They both come from uniform convergence, okay, but they are different concepts. And of course, right, I mean, PAC-C learnability implies PAC learnability because working without constraints is a particular case of working with constraints. Okay, let me now move on to, you know, rediscuss some of the examples that we presented earlier on. Here are two of those, and both of them are related to fairness. On the left, there's the example of predicting recidivism. On the right is the example of predicting income without discriminating between men and women. And let's talk about recidivism for a minute, okay? So this is society, and you can see that society is biased. This is an unconstrained learning solution predicting recidivism, and you see two things. First off is that the learned solution replicates the bias of society, and actually not only that, the learned solution exacerbates the bias of society. How could you solve this problem? Well, you could solve this problem in this way, right? You could say, well, I'm going to condition on individual races, and forgive me here, right? I'm a man of the 21st century, right? So I do not really believe that humanity can be classified in races, but well, nevertheless, this data set is divided in races, okay? In any case, here what we are saying is the following. We are going to require that every individual group doesn't deviate from the whole population average by a significant amount. Working with indicator functions is difficult. Therefore, instead of indicator functions, we can work with sigmoids, and this is more or less the same optimization problem. And observe what I told you before, right? I mean, these sigmoids are not convex functions. The parameterization that I will use is non-convex. Nevertheless, our theory applies because I didn't require either of these conditions in the theoretical results. This is what happens when you incorporate these constraints. So you end up not eliminating the biases of society, but you end up mitigating the biases of society by a little bit. And some other very interesting thing that happens is this. When you look at the unconstrained problem, it has accuracy 68%. When you look at the constrained problem, you have accuracy 67%. So you have really paid little price for enforcing fairness here. And the reason why this happens is actually very interesting. So here is the confusion matrix, and I want you to focus in these cross diagonals. Okay, so this is recidivism for Caucasian individuals, and at the top we have recidivism for African American individuals. And what happens in the case without constraints is that you give a little bit of a slack to white people, you don't give, to Caucasian people, you don't give any slack to African Americans. When you impose constraints, that flips. And what happens is that instead of giving a slack to Caucasian individuals, you give some slack to African American individuals. And that's remarkable, right? Because you do that without any price on accuracy. I mean, you are just being just as accurate. However, you are being just as accurate by reducing the discrimination across different groups. Now, let me talk now a little bit about this problem of predicting income without discriminating between male and female individuals, or individuals that identify as male and female. And in this case, what we are showing is the following. So what happens to the income prediction when we artificially switch the gender of a person in the data set? Perhaps this is easier to see mathematically. We introduce this constant here row, and this constant, or this action row, and this action row flips the gender of an individual. When you flip the gender of an individual, your income predictions change by a quantity in the order of 10%. And of course, right, I mean, this is, by the way, this is not spurious. I mean, that's society, okay? But you don't want your learned solution to replicate the biases of society. Therefore, you can introduce the constraint that the KL divergence after flipping the gender of an individual is the same as the KL divergence before flipping the the KL divergence between the distributions before and after flipping the gender of an individual is close to zero. And you can do that in two different ways. You can do that at the level of the population average, or you could do that at the level of each individual. So this would be what I call point-wise constraints. This would be population average constraints. And what do you see here is that indeed, with either technique, we succeed at eliminating this undesirable behavior of changing the merit of the prediction when we change the gender of an individual. And again, we see the same phenomenon that the accuracy doesn't change that much, right? Actually, as a matter of fact, the accuracy becomes even better when we use point-wise constraints, although, those changes from 80 to 81 to 83 are not statistically significant, but in any case, without pain in terms of performance, you're able to enforce some level of fairness. Now, one final interesting thing that I want to say about this experiment has to do with these Lagrange multipliers. Because these Lagrange multipliers, as I told you, they are controlling statistical generalization accuracy, so it is apparent that they have very important information. So what is the information that these Lagrange multipliers contain? Well, these Lagrange multipliers are telling me how difficult it is for me to satisfy that specific constraint. And here, I am looking at enforcing conditions across all of the individuals in the population. And for that reason, each of these Lagrange multipliers is associated with a particular individual. Therefore, I could say how difficult it is for me to enforce fairness for that particular individual, okay? And when you analyze those lambdas, something interesting happens. First off, 96% of these multipliers are zero. Okay, so for the vast majority of the population, there's nothing you need to do to enforce fairness. But for some members of the population, you do. And it is somewhat interesting which are the members of the population for which this happens. In this plot, when you see the orange bar being taller than the blue bar, what happens is that for that category of individuals, we observe large Lagrange multipliers more often than what you would expect based on the proportion of the population that they are. Okay, so the orange tells you how many members in the data set have this property. For example, how many members in this data set are married. That's the blue bar. The orange bar tells you how often this category appears among those people that are associated with large Lagrange multipliers. And for example, you see something like, married people require stronger Lagrange multipliers. People with master's degree require stronger Lagrange multipliers and whatnot, right? And you can probably guess why this is happening, right? I mean, this is probably the fact that women pay marriage penalties. This is probably the fact that society doesn't really expect women to have master's degree. Therefore, when a woman has a master's degree, that shouldn't happen. I don't know how to say this without sounding like a bigot, but it's difficult to talk about these things, I believe. Okay, I have 12 minutes left, according to my calculations. So let me move on to talk about algorithms for 6 minutes, and then finally to talk about resilience for another 6. Okay. What I have told you so far is that in order to solve these optimization problems, which, we could formulate using this empirical constraint formulation, that problem, I didn't really tell you is a good problem to solve, but, let's look at it for a minute and say which are the algorithms that we could use to solve it. Okay, so one thing you could do is you could use a projection-based method. Another thing that you could do is you could use interior point methods. None of these are going to work, and you can't convince yourself easily because it is very difficult to evaluate the interior point, right? So we are utilizing stochastic samples. So if you are doing a stochastic sampling of a data set, enforcing an interior is very difficult. Which tells you that pretty much the only algorithm that you can use here is a dual learning algorithm. I mean, that algorithm is tractable, and, I have just shown you can move into the dual domain with a loss of optimality. Okay? So, in terms of algorithms, there's like this nice match, correct? Which is that the algorithm that I know I can use in this setting is the algorithm that is guaranteed to work, in a sense. Anyway, so that's the problem that we're going to solve, right? Instead of solving this constrained empirical, instead of solving this primal empirical, we're going to solve this dual empirical, and we know that this dual empirical is a good proxy for the statistical primal. In order to solve this optimization problem, we minimize the primal, And as is well known, the Lagrangian minimizers are associated to a gradient of the dual function, by which I mean that we can compute gradients of the dual function by evaluating the constraint slacks at the Lagrangian maximizers. And that's it. This is the dual learning algorithm, which contains a primal iteration where you minimize the Lagrangian, right? So that's unconstrained learning, so you should know how to do that. Then you go into the dual domain and you perform gradient updates. The dual function is convex because dual functions are always convex, irrespective of whether the optimization problem is convex or not. And as a consequence, it is ready to show that several iterations of this algorithm will bring you close to a saddle point of the Lagrangian. And that saddle point is what we are going to call a solution of the constrained learning problem. Just a couple of things in practice, okay? Doing a gradient update on the dual, that's not difficult. Minimizing the primal, of course, is difficult, right? Because, the primal is a machine learning problem with non-convex parametrizations, etc. So in practice, we don't really minimize the Lagrangian. What we do is we run several gradient descent steps. And, that's how the algorithm will look like. So here there's two nested loops here, right? I mean, the outer loop is optimizing the dual function. This inner loop is optimizing the Lagrangian. And here you could use stochastic gradient descent. And here, by the way, you could also use stochastic gradient descent on the constraints. There's several other things that you could do in practice. Here you can use adaptive methods, for example, Adam. You can, actually, it's not that you can, you should use different time scales for the primal and the dual. That's because the convergence of the dual is subsidiary to convergence of the primal. And, if you ever need to check convergence of these algorithms, it's important that you remember that what we evaluate to test convergence is what we call complementary slackness, which is another way of calling the duality gap, which is the product of lambda with the constraint violations. This is the typical behavior of these algorithms. There's 4 curves here. And I am showing you these curves because if you try this algorithm, sometimes one is squeezy about whether these things are converging or not. But this is the typical behavior that you will observe. Your duality gap will typically grow, then it'll decrease, and then eventually it will converge towards 0. And it could be, guys, that there are several of these oscillations, okay? So you will see this oscillating behavior typically. What is perhaps more important is what happens with the slacks. You should observe these slacks to decrease and become negative. Then maybe they will become positive. You can see some oscillations there as well. And something that is actually very typical and is not really always the case with primal dual methods, but it is the case with constrained learning in general, is that very often Lagrange multipliers grow and then they decrease. Why this happens, we don't know, but this is, of these 4 plots, this is the only one that is an empirical observation. The other 2, that's always the case when you run these primal dual optimization algorithms. Okay, I'm gonna give you like a 30-second appendix. Before I give you that 30-second appendix, let me summarize the things that we have said actually with Luis. Fact number 1, this learning with requirements, learning with constraints, constraint learning problems, they appear everywhere. So, we hope that we can convince you to investigate the kinds of problems. I mean, particularly in controls and engineering, right? I mean, in controls, you never say, I want to minimize a cost. You always say, I want to minimize a cost, I want to be safe, etc. So there's a bunch of things that you want to satisfy. So you should really be thinking about formulating problems with constraints. Second thing that we told you is, okay, are these problems solvable? Because that's an important question, right? I mean, okay, we can write down learning with constraints. Is it possible for us to solve these problems? Do these problems have meaning? Well, that question is, do the empirical generalize to the statistical? Well, the answer to that question is yes, with several caveats, perhaps. caveat number one is that you need a parameterization that is sufficiently rich. And caveat number two is that the difficulty of the requirements gets mixed into the picture in the form of the optimal Lagrange multipliers. Now, fact number three that we covered is the use of this primal dual learning algorithm. This primal dual learning algorithm it's not our contribution, right? That's a standard algorithm. It's based on minimizing the Lagrangian followed by gradient ascent steps on the dual. And however, despite a number of complexities like lack of convexity mostly, right? It is still possible to show that this primal dual algorithm will converge to a saddle point of the Lagrangian. This, by the way, is very important, okay? So non-convex optimization problems are the least interesting problems in the world because you can't write them down, you can't solve them. In this particular case, I am writing a non-convex optimization problem, and I have developed the theory that allows you to claim that, yes, you can solve this problem. Furthermore, it generalizes to the statistical. Okay, that's maybe the message that I want you to remember. Even though these problems are non-convex, you can, A, solve them, B, generalize them to the statistical. And if you do all of that, I think you obtain something very interesting, which is a behavior that is very different from the use of penalties. Because these things generalize in very different ways, okay? If you have a penalty-based learning problem, that's the generalization that you have. The loss plus lambda times the penalty, empirical and statistical, these two things are close. In dual learning, what generalizes is the penalty is constrained. See, this is very different, right? I mean, I give you a weighted objective here. In the empirical, maybe in the statistical, the loss and the penalty, they could be very different. Actually, I can give you examples when the statistical loss and penalty will be very different from the empirical loss and penalty. If you're solving a problem with penalties, your statistical claims become very weak. They are on that sum. And that sum, is something you concocted. However, here we say generalization in a very different way. We say generalization means near optimality and penalty controlled by C, which is a quantity that you have designed, and it is the same quantity whether you're looking at the empirical or the statistical, meaning if you can guarantee that the penalty is small in the empirical, you know that it will be small in the statistical as well. I will eat one of your minutes, Luis, to talk about resilience-constrained learning. There's something I haven't told you about. Let me try and illustrate this with an example. So this is the heterogeneous federated learning problem that we described earlier on. So here we have individuals with different class distributions. Okay, so, you can think of this as voice recognition. So this is, whatever, standard English speakers. This is KG with a Greek accent. This is me because I speak with a Greek accent too. This is someone that speaks with a Hispanic accent. Okay, so these are, different individuals. They have different data sets. They want to collaborate to improve the quality of their classifiers, but they want to collaborate only if they don't have to pay a penalty in terms of their own performance, okay? I mean, I don't want to share my data for my classifier to become worse. I mean, I want to share my data for my classifier to become better, okay? Well, we can formulate this with constraints, okay? You can question whether this is the right problem formulation, but in any case, you can impose constraints that tell you, well, yeah, we are collaborating as long as we all gain. But in that problem formulation, we have a value here, which is C. And the question is, is this C realizable at all, yes or no, right? Because I can impose whatever constraint I want, but my data is what tells me which constraints are feasible. So specifying constraints is not so easy in constraint learning, okay? And that's what brings us to these notions of resilience, which is a way of automatically tuning constraints levels when we have constraints violations. And by the way, we call this resilience because it is very similar to the concept of resilience in ecology, okay? We say that because people ask us, why do you call this resilience? Well, because if you look at the definition of resilience in ecology, it's essentially the same. Now, what do we mean by that? Well, that's the problem that I would like to solve. I am going to introduce a relaxation. When you introduce a relaxation, something interesting happens, by the way, which is that relaxations are good from the point of view of the objective. But of course, relaxations are bad from the fact that you are relaxing your constraints. So relaxations, which in this case we call resilience, are a compromise between the benefit of the relaxation and the cost of the relaxation. And when you have to, settle a trade-off, you can say, well, the benefit is how much I improve my objective. The cost, well, I am going to define that by a function h of r, and I am going to say that the resilient equilibrium is the point at which the marginal costs and benefits of the relaxation are equal. What is the behavior that we are going for? Because perhaps that's more interesting. This is how the derivative of the relaxation benefit behaves, meaning how much your constraint improves as you, how much your objective improves as you relax the objective. And there's a minus here because remember, right? I'm minimizing. So improvement here means the cost becoming smaller. And here's the price that I have decided I will pay for violating this constraint. This is an optimization problem in which the constraints are not difficult to satisfy. Therefore, my relaxation is minimal. This is a problem in which the constraints are more difficult to satisfy. Therefore, my relaxation is larger. And this is a problem in which the constraints are very difficult to satisfy. Actually, they're infeasible in the original problem. And for that reason, I relax my constraints quite a lot. As you very well know, that derivative equals the optimal Lagrange multiplier. And by the way, that's the reason why those optimal Lagrange multipliers appear in a statistical generalization, because Lagrange multipliers determine the sensitivity of the optimization problem. And it is therefore not unreasonable to expect them to appear in a statistical generalization result, because a statistical generalization, at the end of the day, is a perturbation analysis. Now, however, I do want you to observe something very interesting, which is that after relaxing the constraints, the Lagrange multipliers decrease. So this resilient problem buys you something for free, in a sense, which is that you have better statistical generalization. Okay, good. And it's not difficult to show that this resilient equilibrium exists and is unique. The reason why it exists and is unique is because I am requiring H to be strongly convex. Okay, now, this is the kind of behavior that you obtain with these resilient solutions. This is the kind of behavior that you obtain with these resilient solutions. So what I am showing you here is, what happens with the test accuracy for different clients as you introduce the resilient generalization. And here in red, I am highlighting deterioration of performance, and in green, I am highlighting improvement in performance. And what you see here is that a few individuals whose constraints are very difficult to satisfy have their constraints relaxed so that the vast majority of individuals can have their constraints improved. Another interesting plot is this one, where we are showing the prevalence of the minority class versus the value of the perturbation, and you see that as we have more prevalence of the minority class, constraints are relaxed more, right? And that's consistent with the statement that more difficult individuals have higher relaxations. And finally, let me show you what is results about a statistical generalization. So these are constraint and resilient constraint violations during training, and these are violations during testing. You see how it is possible for some individuals to be quite far from what the training set predicts. And that's because these Lagrange multipliers are very large, but when you have resilience, you have better generalization because your Lagrange multipliers are small. That concludes what I wanted to say, and I think that we're going back to Luis now, or we're going to the break. KG? Yeah.
Thank you. Actually, I should have said that my part is very adaptive, so I'll just skip half of what I was going to say. It's not important. Anyway, yes. So as Alejandro said, it's hard to give a talk after lunch. It's even harder to give a talk after lunch when everybody's jet lagged. So we're doing the best we can. And you too, thank you. You know what? I'm going to hold it because I'm tired. Okay. So for the next, roughly 20 minutes, I want to leave some time for questions. I'm going to talk to you about essentially robustness. So all the theory that Alejandro developed, right, is going to continue to hold. But there are a couple of things that I want to show you how essentially we can use constrained learning to do something that is not constrained, right? To something that is not really constrained learning per se. So this is the idea of what we're going to talk about, which is specifically developing a theory for how can we deal with robustness constraints, okay? So I might not get to this probabilistic robustness. That's not very important, but I want to be sure that I get through the first 2 points. So the first one is about adversarially robust learning. So this is the problem that I mentioned in the beginning, right? So we have this, we can train classifiers to, classify images. This is pretty, in quotes, easy at this point. You can do it sort of taking some off-the-shelf model, and you can achieve very high performance on typical benchmarks, except for the fact that, the classifiers you obtain are quite brittle. So if you modify the input just a little bit, you get very different performances on the, than, on the clean data set. And this is sort of the problem we want to mitigate here with, by changing how we measure the performance, right? So the way to do this is rather than training on some clean data, I'm going to train on to be good on the perturbed data, right? And hope that I also get good on the clean versions. And what we see as a plot is that indeed we improve a lot our robustness, right? So we become much better at resisting perturbations of the input, right? Except for the fact that we have a little bit of loss on the clean data because we don't get to see the clean data at all, right? At this point. So this is sort of this type of trade-off that we're going to have, and we want to deal with this essentially. And the typical way to do this, and this is the point where I want to, refine a little bit what we said before, is to use, regularization. And there's nothing wrong with this, right? You add a penalty there, and if you add a penalty, you actually can get very good results in the sense that you can, for the exact same, let's say, nominal accuracy, so accuracy on clean data, you can get even better robustness. Okay, so you can achieve a better trade-off between these two things. So it's not to say that, that regularization is not a good idea. It's just that to make this work, first, it takes a lot of adjustments of this lambda, and it's also very problem dependent, right? So this is the thing that we want to avoid. Every time you change the data or change the losses here, you have to go and retweak what lambda is. This is the thing that we don't like. This is the thing that we don't like about this formulation is that it's very, it requires a lot of re-engineering every time. And so, we landed on this better idea, which was to use constrained learning to achieve that trade-off. And essentially, the idea here is to use, a value that is not dependent on the relative value of those two losses. It's sort of exactly the measurement of our loss. So it's a problem dependent rather than an instance dependent value. And using this, we can get, for essentially the same nominal accuracy, a slightly improve on the robustness. That slight improve is really not the point here that we want to drive, right? I mean, this is very, very little, less than 1%. But what is important for us in this case is that we know there is a trade-off between these two problems. And it turns out that by using constrained learning, which is this orange curve, right, we get to achieve better trade-offs than the ones that you would accrue, so dominant points over the ones that you would achieve with a fixed value of a penalty. And the reason for that is what Alejandro mentioned, right? Is the fact that these two problems are different in the sense that here, what we are choosing is a fixed lambda. In constrained learning, lambda is a inner state of the algorithm, right? It's something we use in order to achieve C, which is the thing that we're using. And that means that the typical values, the typical plots that you get look like this, right? They look like, in the first part of training, we are still above, let's say, the constraint that we want, right? So, you know, the value of lambda keeps growing. And then afterwards, once we achieve the specific constraint, the value of lambda decreases. And what happens at the end here is that the value of lambda is essentially 0. It's very close to 0.05 or something like that, right? But we know that if we start training with a lambda of 0, we don't get a good result, right? We get essentially this result here, right? Sorry, this orange curve. We know that's not a good idea. So it turns out that even though the value of lambda at the end is 0, this during training is important, right? It's an empirical observation that has been done a couple of times. What is interesting here is that we don't need to know that this is important in this particular problem. This is just the algorithm. It's a property of the dynamics that we use to solve the problem, okay? So, I'm going to skip this, it's not very important. So it turns out that, you know, we sort of dealt with the problem of balancing nominal accuracy and robustness using this idea of constrained learning in a way that is, you know, certainly beneficial over using a fixed lambda. But one of the problems that were sort of swept under the rug, which is exactly the thing that I want to talk about now, is how do we go about computing these worst case perturbations? Okay. And the reason for that is that, you know, this, as Alejandro pointed out, is a non-convex problem. And in the case of computing the worst case perturbations here, it's even an under-parameterized non-convex problem. So it's typically the good stuff that, you know, the good landscape of optimizations, all these good results, they're not going to apply here. So we're in a very, let's say, challenging setting in general. So the way we can deal with this, typically, the way that is dealt with this is by using projected gradient descent, which is the case that we know is not good in this case, but, you know, it works quite well. And the idea is just that, you know, we just find a specific perturbation by using projected gradient descent and then do our descent step at the end, okay? And, you know, for this to work, you need a lot of different techniques like restarts and random initializations, exactly for the fact, due to the fact that, you know, this is not an easy problem. It's a very challenging non-convex problem. Contrary to constrained learning, which was, you know, turned out to be a manageable non-convex problem, right? So what we want to do is try to deal with this problem. And the technique that we're going to use, as I mentioned in the beginning, is to use constrained learning to try to solve this max problem. So the idea here is to use constrained learning as a tool to do something that is not constrained learning, right? And this is where comes the idea of semi-infinite learning, okay? Semi-infinite constrained learning should be more correct. And the idea here is, again, something that you saw this morning, which is, that Daniel was mentioning, which is to use an epigraph formulation, okay? So we're going to take this max problem here and transform it into a epigraph problem, okay? What all this means is that, you know, for the maximum of something to be less than a value means that all of those values are less than that value, okay? This is the only trick we use here. So we replace a max by this sort of, constraint that are here, right? Now, because we need this to be less for every value of delta, this constraint problem is actually what we call a semi-infinite constraint problem, right? Because you need one of those values for each of the deltas. And I didn't use numbers here because actually, I mean, this is a infinite in the sense that of continuous, right? Not that there are an infinite number of discrete values. Okay. So how could we go about tackling this problem, which is a problem that, you know, has appeared a lot of times. This is related to scenario optimization, for example, in control, right? So what we want to do is, again, to use duality. Okay, so I essentially showed this first step here, right, where we go from the primal problem to an equivalent constrained but primal problem. And now we use duality, not duality, but a Lagrangian formulation to rewrite this problem as this Lagrangian primal problem. It's still primal because I haven't really, you know, switched the sup and the min and the max, right? This is the important part that we want. And we will actually never do this here. But the point is that these two don't need to be swapped for now, at least. Okay, so all of these are equivalent. And the interesting thing is that now, because, this problem was continuous, we get this continuous dual variable. And this continuous dual variable turns out to be a probability distribution. So I can replace that with an expectation, actually. Right? And this is the thing that we want to leverage. We want to leverage the fact that this expectation here is one that, has nice properties so that we can sample from that distribution. And this is how we get to this proposition, which is essentially using, again, constrained learning to do something that is technically unconstrained learning. Right? And what we say is essentially that you can find, a class of distributions here. We can characterize this optimal distribution here. For any approximation level that you want, you can find a different one. And what these distributions look like, which are written here in closed form, is essentially truncations of the loss. Okay? So essentially, if for different values of gamma that I pick here, I remove, let's say, the easy values, right? So I'm trying to sample from things that have higher and higher loss, right? And that's the idea. And, in the limit, what we get is exactly the max. That's exactly what we want. That's extremely hard to sample from. That's the original problem we're trying to solve using projected gradient ascent. So that's not a good problem for us. So, but there is one problem that is easy, which is this problem, which is to sample exactly equal to the loss. And the reason for that is because, our losses are nice losses. If they are L2 integrable, this is a problem that we can actually sample very easily from using MCMC techniques. Right? And this is an approximation of the max, but it's an approximation that we can characterize or at least guarantee that, at least we're going in the right direction of the problem, right? Rather than saying, do the best you can with projected gradient ascent. Okay. So now, essentially, we're going to replace that max with an expectation, which, as Alejandro has mentioned over and over today, we can actually solve using stochastic gradient ascent, or in other words, using samples. And then the challenge is just how do we find the samples from that distribution? Okay. So that's exactly the result you saw before, right? These results actually use not only constrained learning, right, to balance these two objectives, but also uses this distributional, let's say, approach to solving the max. Now, it's important to say that what I am saying, what the theory says here, is not that this distribution is computing the max of the loss. It's just that the minimizers are the same. Right? It's very important because otherwise, we know that if you want to compute the exact value of this loss, in other words, to find the max, the delta that achieves the worst case scenario, then in this case, you need to solve the maximization problem. All this theorem is saying is that the minimizers of the two of them turn out to be the same. Or, in our case, to be an approximation. Right. And the reason here, this is just to illustrate a little bit what happens when you use, projected gradient ascent with random restart and sampling, the big difference between those two. You can see here, so this is for the MNIST data set, we have the two first principal components. So these are the directions of largest variance in the data, right? These are the first two modes, let's say, of the data set. And we can see here the disturbances projected on those modes. And we can see that while, projected gradient, PGD is, for some historical reason, projected gradient ascent was called PGD. I continue to use anyway, I don't want to comment on this. So this is just the naming of the algorithm, right? So this is projected gradient ascent, not descent. I just wanted to make this asterisk here is important. So, if you project the disturbances you get using projected gradient ascent on these two principal components, you can see that it uses a lot of energy in the second component, which is not the largest variance, it's the second largest variance. It's still pretty good. It's not a bad idea, but it's not the best way to do, which would be to concentrate more on the first direction. And that's exactly what, if you use sampling, actually does, right? The sampling has the advantage that, it exploits a little bit better this first component that we wanted. And the reason for that is that, as you will see, the algorithm is very similar to projected gradient ascent, but it's not exactly the same, right? Because it's based on MCMC, it's based on Langevin dynamics. And this is the algorithm that you use. So essentially, we use a, HMC sampling method. Essentially, we run a couple of iterations of this. This is to obtain a sample from that distribution that we had before. And then we do stochastic gradient descent, followed by gradient ascent, which is the last step of constrained learning, right? And what is interesting, and the reason why we use this algorithm that is interesting, is because this first step here, which is just sampling from a distribution, right? It's just one way. You could find different ways to do it, but this specific way connects to a lot of other proposed algorithms for this specific method, right? For example, we could pick any distribution we want here. So we can pick any distribution we want here to sample, say, a Gaussian or some patches, right? And these are algorithms that have been there. Those are suboptimal choices of a distribution to sample from, right, compared to the one we mentioned. Or, for example, if we essentially remove the noise that is here from the Langevin dynamics, in this case, we're doing projected gradient descent. We're not sampling. We're just trying to find the worst case scenario. That's exactly that algorithm that I call PGD, right? So ultimately, what we're doing is we have a more general framework here that is based on constrained learning in order to solve this type of problems that leads to an algorithm that actually, a lot of people have used before, have investigated, have looked into it. And the advantage here is that rather than doing, let's say, heuristic random restarts, we have, a justification for that randomness that comes from the fact that we're actually trying to sample from a distribution. We transform the max problem, the worst case scenario, into sampling from a distribution. Okay. So the last thing that I want to spend a little bit of time is to talk about that problem that I mentioned in the beginning, because, okay, we talked about robustness in vision, but, there are other problems that can benefit from robustness in ways that are not directly robustness. And one of them was smoothness, right? Lipschitz property is a robust property of a function in a certain sense, right? So we can think of this imitation problem where we see some actions related to some states and we want to find a controller that essentially reproduces those actions at those states, right? It's a very simple problem in this case, the two-dimensional, very nice, but if we are in a larger state space or in a more abstract state space, it would not be less easy. And the idea here is that we don't get a lot of data, and we want to know, what happens in the other spaces, in the rest of the space. And this is a problem because, if you take just do simple, let's say, linear regression, right? It's not linear, but it's like just regression, just regress the state on the actions. This is the type of behavior you get, right? This is the controller that you get. And you can see that there are regions here where essentially the control, there's nothing. And the reason is we have no data here, so we have no idea what we have to do. And the bias of this specific model was to just do nothing there. That means that if I start in this region, I might not go in the direction that I need in order to actually get to the object. And that's why, the number of success is 85%, which is not bad, but it's not as high as we wanted. And what we want is essentially to leverage this unlabeled data. And the unlabeled data we're going to see here are points that belong to the free space. Right? And as I mentioned before, what we want to, in a certain sense, is for this controller to be smooth, or in the sense that the actions that it predicts for each state to not be very different for states that are close, but not close in Euclidean space, right, between these 2 points, but close while navigating in the free space. Which again, here is quite easy to see, but in an abstract case, it might not be as simple, right? So if I have 2 points, one on each side of this barrier, I want to consider their distance to be, going around the barrier, not just the distance between the two actual points. And that's why we have points in the free space, right? They sort of describe that barrier there. And what we essentially use to do that is that we're going to create sort of a low-dimensional structure here, which in this case is going to be a manifold, or an approximation of this manifold based on, this unlabeled data by using, the Laplacian essentially approximation of this, and used a constraint optimization problem that tells us, okay, you need to fit the actions to the states, but at the same time, the actions that you take for states that are close by should be similar. But states that are close by in the distance on this manifold, right? So taking into account the free space as information. And the free space is given as information only through data, so through points of the space, or a grid of the free space. And again, we're going to replace this max by this expectation. And what we get then is a solution that is smoother in the free space, right? And that actually achieved 95% success. Okay, so it's a 10% increase. Now, if you were to use just the regular distance without the manifold part, right? So let's just use the distance between the states regardless. The accuracy, the success rate is actually in between those two, right? So it uses information, that's good, but it doesn't use the information the way you need to use it because it's unable to consider, these barriers that are in the middle as information that we want to also give to the control. Okay. So in the interest of time, I'm going to skip probabilistic robustness. I'll just give you a taste of what it means. Essentially, the idea here is that, we know there's a trade-off between adversarial and clean accuracy. The way we dealt with this was using a constrained learning problem. But there is a different way to deal with this, which is to just maybe don't require things to be as robust, right? Like a bit less robust. So one thing that was mentioned this morning, for example, are these LQ norms, right? So we can maybe, rather than being robust L infinity, we can be LP or something in between average, right, and max. And what we do here, these are the idea of probabilistic robustness is just to replace this max by a chance constraint, right? So rather than being robust to every possible perturbation, I'm going to say I want to be robust to 95% of the perturbations. You can choose which 5% you throw away, but that's a 95%, right? And essentially we use this, so this is the definition of this tau essential soup. So it's the value that is higher than 95% of the points of the function. And we can connect these to the risk aversion literature by showing the C-var is an approximation of this. And then the results you get is essentially that the nominal accuracy for these methods that are probabilistically robust is much higher than those that require the maximum robustness. Obviously, against the worst case perturbations, they are just as bad. But against 99% of the perturbations, they are much better. Right? So there is this idea that the worst case actually demands too much because of very little things. Right? There is 1% of the perturbations that are actually terrible, but 99% of them are fine. So we're wasting a lot of trade-off on that. This is just a different way to define robustness that is, again, related to constrained learning through the idea that, once we look at this problem as a semi-infinite problem, I could say, well, just remove some of the constraints, right? Which is the idea of what Alejandro also mentioned in terms of resilience. Some of the constraints, we're just going to relax them. And we relax the hardest ones. Okay, so just to conclude, right? The idea here was to use semi-infinite learning, or let's say constrained learning, in a different way than before. We want to use constrained learning both to, trade off between, let's say, worst case and nominal accuracy, but also to solve the problem of finding those worst case problems. Okay, so what we're trying to do is use it in a slightly different way to tackle these issues. And again, that's how we developed this algorithm of for replacing the max with sampling by using duality once again, or Lagrangian duality. And then we can use in connections to other rooms of the literature to also do that. Okay. So I'm gonna stop here for questions. Thank you very much.
Here, because you can ask questions about any of them.
Yes, this
Three
is
pieces
yours.
of it.
Thanks. Doesn't work.
It works. Yeah, it's working.
It works. Okay. Just I don't hear myself. Thank you. Very interesting both presentation. I had a question for you. It's one of the last things that you show where you were learning this behavioral enforcing some smoothness. I was wondering, were you considering only the obstacles, or are you considering also the dynamics of the system?
That's a very good question. In this case, we don't consider the dynamics. That's the point of doing imitation learning, right? I have no idea what the dynamics are. Right? Just the only thing I have are, those points there that says at this state, take this action, right? The, let's say, optimal manifold to consider in this case would be the manifold of the dynamics, obviously. If I had access to that, then the problem would be solved as well, because then I would have access to the controller, to the manifold of the optimal controller that does this trajectory, right? I could think about, having more trajectories, identifying the dynamics, and maybe use the dynamics to build the manifold. This could be very interesting, especially if you identify the dynamics in ways that, if I know it's a linear system, then I can use a linear system as well. That's like doing a projection, that all of that is extra information. Again, all these things can be added as extra constraints on the problem, right? There is no reason to remove this constraint. You could just add another one that has the dynamics in there. If it's imported, it will be taken into account. If it's not, then the lambda will be 0 and all is good. So I think that's a very interesting question.
I can add something to this answer. Yeah, that's a paper we haven't written. You should write it. Yeah, what is interesting here is that instead of imposing Lipschitz continuity in the ambient space, which is what most works would do, we're imposing Lipschitz continuity on the manifold. Right? We do it in the geometric manifold because that was easy for us to do. But if I understand you correctly, what you have in your mind is to impose Lipschitz continuity on the configuration space. And that's where you should impose it. I agree with that. It's just that it's not the focus of this paper.
I have a question for the initial part of the talk. And there, you go this way from the primal problem to use the augmented Lagrangian method. I wanted to ask how you mentioned that the infinite dimensional case is often you have strong duality there, or how important that is, or is it just something you observe in practice, or what kind of criterion you really have on these methods?
Yeah, that's a great question. Let me find the slide and let me try and explain. Try and answer your question. So just that everybody's on the same page. Let me repose your question. What we are doing here is the problem that we want to solve. It's a problem. It's a problem with constraints. It has a parametrization, and and it is statistical. That problem I don't know how to solve. Okay, this one here at the top, which is has a parametrization. It is dual, and it is empirical. I know how to solve because I have my data. I will introduce my parametrization. I will do primal dual on that. So I discuss this algorithm later on. So the question is, this is the one that I would like to solve. This is the one that I can solve. And I would like to claim that they are close because, this one is close to the constraint empirical, and this is the dual version of the constraint empirical. Unfortunately, I don't have learnability and I don't have duality. And that's why I took this long route. And, you understood all of this. So I'm going to get to your question in a minute. I'm just trying to, to get all of us on the same page. So then I went through this other route where I said, well, let me remove the parametrization. And then after I remove the parametrization, I can show that there is no duality gap. Then I can go back up by using the richness of the parametrization. And I can go, one step further up by using a standard statistical learning theory. Now, you don't need a PhD for this step. You don't need a PhD for this step. You probably need one for this step, which is the one that you're asking me about, okay? Now, in this problem, there's two things that could happen, okay? Maybe L and G here are convex functions. If L and G are convex functions, well, then this is a convex optimization problem, and it has no duality gap. Yes, it is functional, right? It is on an infinite dimensional space, but, as long as this is Hilbert, there's no duality gap here. But I say something more, which is that I don't require convexity of L or G to make this claim. And the reason why that holds is because we are assuming this parametrization here to be non-atomic, okay, which means that there's no deltas in this distribution. This is like a proper distribution. And when that happens, these kind of optimization problems, they have no duality gap. And this is related to something that is called Lyapunov's convexity theorem. So it's a different Lyapunov than the one you all know. By the way, this one is A.A. Lyapunov. Whatever. Anyways, there's something called Lyapunov's convexity theorem. It's a theorem about measures in function spaces. And when you have measures in function spaces, you can prove convexities of some ranges that allow you to claim this lack of duality. Yeah, and by the way, since we are controls people, I mean, the first place where I know these results have been applied is in reinforcement learning. This is like around the year 2000. People utilize this Lyapunov convexity theorem to show lack of duality gap. Sorry, lack of duality gap in some MDP problem.
In control, this is used sometimes in if you have seen proofs for bang-bang controller optimality, that's the same Lyapunov. You can do it using Lyapunov convexity as well. So it's related to the same idea that, the caricature of the result is this one that is on the screen, right? If you have integrals, the non-convexity is not as important, essentially.
If you're interested in the mathematics of the result, I mean, the reason why we pointed to this paper here is because this is like a very simple problem, because here you have a summation of indicator functions, which here you replace by an integral of indicators. So this is very clearly non-convex, and this is kind of like of all the proofs that we have done using Lyapunov's convexity theorem, this one is the easiest. So if you want, or the cleanest, if you want to learn this mathematics, I would look at this paper.
I'm also a quick one. So first of all, thank you for the talk. So I'm looking at your algorithms when learning with constraint, and I realized that whenever you update the Lagrangian multiplier, like the lambda, it requires kind of you have to calculate it with respect to all the samples. So I was wondering, is it possible to say maybe in some sense kind of further truncate the complexity to just doing batch samples, or in reality, is there a way to compute it in a more computationally
the short answer is yes. The longer answer to the question that we are asked here is the following. So we are summing here over the whole data set. That's because we're implementing gradient ascent on the dual. The question is whether you can implement a stochastic gradient ascent. The answer is yes, of course. You don't need to sum over the whole data set. In practice, we don't do that. We sum over portions of the data set. Furthermore, you don't even need to use a stochastic gradient descent here. You can use something like Adam. So, this is, what is important is this. This G here, that's a stochastic gradient of the dual function, okay? And once you have that, you can plug that in whatever is your favorite stochastic optimization method.
There are many ways to improve the complexity of these. You can you can alternate between the two with different time scales, like Alejandro said, in which case you just need to run one batch through everything once. Again, this is just to show one example of the possibilities, but we can talk about this offline as well.
And one other thing, I mean, we're all researchers, so this is, there's a lot to do on developing good methods to maximize this dual function, right? I mean, there's momentum methods. The dual function is convex, so you could use stochastic quasi-Newton methods here. I mean, there's quite a lot here that can be done in terms of optimizing the dual function, which we haven't done.